Today we're going to take a look at lesson 4.2, isosceles and equilateral triangles. Lots of different triangles out there in the world. This lesson is dealing with two specific ones. What makes an isosceles triangle, what makes an equilateral triangle. There's certain properties that define one versus the other. And we'll cover both of those here in a little bit. So let's go ahead and start off with example 1. Understand angles of isosceles triangles. So they want you to sketch an isosceles triangle ABC. And what they're getting at here, there's lots of kind of algebraic definitions like, the line BD, the angle ABC. You can see this right here, reflect line BD. Across line B to give you B. So there's a lot of kind of algebraic stuff happening. So let me simplify what's going on here. What they're doing is they're saying that an isosceles triangle has a property to where, let's say, this bottom half of this triangle would mirror itself across that line and it would lay right on top of the top half. Okay. That doesn't mean that all these angles are the same, but what it does mean specifically that these two base angles have to be the same. Okay, so this triangle can be super tall, it can kind of be short, but the two main properties that you have to know with isosceles triangle, that's going to deal with every isosceles triangle you look at, the two base angles are going to be congruent, which based off of lesson 4.1, that means equal. So in this situation, angle A has to be equal to angle C. And the other thing that's always true with isosceles triangles is that the side BC is going to be congruent with the side BA. They're going to be the same length. So those are two properties that define an isosceles triangle. Your two base angles have to be equal and your two side lengths have to be the same, congruent, right? Again, there's lots of kind of algebra happening here, so don't let it confuse you. Just keep in mind the two base angles have to be the same, and the two side lengths have to be equal. They have to be congruent. Unless on page 158, we've got a theorem, theorem 4.1, isosceles triangle theorem, and the converse. So what this is really getting at is sort of kind of emphasizing the idea of the property we just talked about with isosceles triangles. If your two side lengths are the same, right? The same length, whatever that length is, if they're the same, then the two base angles have to be the same. And then the converse of that statement, basically the opposite, if the two base angles are the same, if they're congruent, if they're equal, then the two side lengths have to be the same. Okay. Example 2, use the isosceles triangle theorem. So an architect is designing a community park between North First Street and South First Street. The pathways on either side of the pool will be equal in length. Ooh, so that's cluing you in, that statement right there. The pathways on either side of the pool will be equal in length. That is meaning you're dealing with a specific triangle here. If they're the same length, that's setting you up as a isosceles triangle. So this side right there, DE, and that side DF are the same length. And will provide effective access and circulation around the pool. To protect the landscaping and to minimize erosion, the architect will place a triangular section of triangular, lots of triangles, right? Cobblestones at the corners along Park Plaza. Which angle measure should the architect specify in the corners for her design? So the reason why this is connecting it back to theorem 4.1 at the top of the page is because we know that if these two side lengths, DE and DF, if those are the same exact length, then these two base angles, angle E and angle F, have to be the same length. Okay, that's just a property with isosceles triangles. That's always true. If the two side lengths are the same length, then the two base angles have to be the same length. All right, so how they're walking you through this is they're telling you that every triangle, doesn't matter what it looks like, it doesn't matter if it's isosceles, equilateral, whatever triangle you're dealing with, all the angles, all three angles on the inside of that triangle have to add up to 180 degrees, okay? So they're kind of starting to replace some information though. So they're saying angle D, they're replacing that with 50. And the reason why is because it's given in our problem right there, angle 50, or angle D is 50. And then they replaced angle E with angle F. What they're doing there is just emphasizing that because these two side lengths are the same exact length, these two base angles, angle E and F, have to be exactly the same amount. So they're just emphasizing that instead of talking about two separate angles, you could replace angle E with angle F, or you could have replaced angle F with angle E. It doesn't really matter. Okay. But the main idea is now you have an algebra problem, and I'm going to go ahead and write this out. 50 plus x equals 180. Sorry, I'm going to actually change that around. I'll do 50 plus x equals 180. Okay. I'm just replacing, angle F with x and angle F with x. So it's just the same thing. So algebraically, how would I do this? Well, I'd combine like terms. So x plus x is 2x. And then I want to solve for x, so I'll subtract my constant from both sides. 2x equals 130. And then solve for x, divide both sides by that coefficient, x equals 65 degrees. So what that tells me is that because these two side lengths are the same, the two base angles have to be the same. We know one of the angles is 50 degrees. So we take the leftover amount, which was 130, divide it by 2, because they have to be equal to each other. So both of these base angles are 65 degrees each. Example 3 at the top of page 159. Use the converse of the isosceles triangle theorem. What are the lengths of all three sides of the triangle? So in order to find these lengths of all three sides, they want you to use the idea of the converse of the isosceles triangle theorem that we talked about at the top of page 158. So their first step, what they're trying to show you here is if you know that this is an isosceles triangle, well, then you know that these two side lengths have to be the same. They have to be congruent, okay? So what I can do is just literally set those two side lengths equal to each other. So x plus 20 equals 8x over 3. That's what they did here in step 1. Do some math. My first step would be to multiply both sides by 3. Then go ahead and solve for x, and I get x equals 12. So I can always go in and plug in these values of x to find out whatever side length I want to. So if x equals 12, 12 plus 20 is 32. So I know that PR, the length of PR is 32. I don't even have to plug it in over here, 8x over 3, because again, this is an isosceles triangle. This length has to be the same length as this side. So if this is 32, this has to be 32. You can do the math if you want to, but unless I did something wrong, it should be 32. And then if I plug this in, x equals 12 to my base, 6 times 12 is 72. 72 minus 12 is 60. So that's how you can algebraically solve that. Just keep that in mind, the property of isosceles triangles, that the two side lengths are going to be equal, and then the two base angles are going to be equal. And as long as you keep those two things in mind, that's going to help you solve these problems in this section. Theorem 4.2, so at the bottom of page 159, if a line or line segment bisects the vertex, so that just kind of means a corner, right? A corner of one of these triangles, that's a vertex. Bisects the vertex angle of an isosceles triangle, then it is also the perpendicular bisector of the opposite side. So this is a property, this is a truth, this isn't asking you if that's true or not. What they're saying is if you have any isosceles triangle and you create a line that bisects that vertex at the top, that line that bisects the vertex and makes the left side equal to the right side for that angle is also going to bisect AC, the base of this triangle, but it not only bisects it, it's a perpendicular bisector. So that kind of means two things. Perpendicular means that it comes straight off of the ground. Basically, line BD is at a 90-degree angle straight off the ground from the base, AC. So that's perpendicular. It forms a 90-degree angle right there. And then the bisector means that it cuts AC perfectly in half. So AD, that line segment, is going to be the same length as CD. Same thing over here, just kind of emphasizing exactly what we talked about. Example 4. Use perpendicular bisectors to solve this problem. A prefabricated house is delivered to a foundation in 2 symmetric halves that are assembled on site. Along the planned roof or route to the site, the truck must pass under a bridge that has a clearance height of 17 feet. Should the trucker plan a different route for delivering the house? Explain. So based off of this given information that they're giving you up here in this diagram, this is where they got that information, right? So they're telling you that the top left part of that roof line, that angle measurement is the same as the top right half. Okay, so they're just kind of insinuating there's a perpendicular bisector that's splitting that in half. And then they're telling you that the left slope of that roof line is the same length as the right slope of that roof line. So basically telling you you've got an isosceles triangle. They're also telling you that the base of that house, the width of it is 28 feet. So just kind of, again, they're giving you the information for you to kind of, derive that this is an isosceles triangle. So there's the picture, create a diagram. That's exactly what they did. Just created exactly what we talked about. And then they want you to use the Pythagorean theorem, right? That's a squared plus b squared equals c squared. So you're dealing with that when you deal with right triangles. Specifically, don't look at the entire isosceles triangle. You're just kind of looking at one half of it. That's a right triangle because that bottom right angle is 90 degrees. So in order to find the height of any right triangle, you can always use the Pythagorean theorem. And I'm going to go ahead and write this down because I don't see it on the page anywhere. So Pythagorean theorem is a squared plus b squared equals c squared. And specifically, this is just a leg. This is just a leg. But this has to be your hypotenuse. Okay. So in this case, you could do A is 14, B is H, C is 16. You could do A is H, B is 14, C is 16. It doesn't really matter where you put A and B, but just make sure that your hypotenuse, the part that's opposite the 90-degree angle, that's your hypotenuse. That has to be your C value. So that's what they did. Use the Pythagorean theorem. It looks like they replaced A with H. They replaced B with the other base, which was 14, and they replaced C, which is your hypotenuse, with 16. Just do the math. 14 squared, 16 squared. I don't know what that is off the top of my head right now, but I know if you subtract 14 squared from both sides, you'll end up with H squared equals 60. And then to solve for H, you'll take the square root of both sides. So the square root of H squared is H. The square root of 60 is root plus or minus root 60 technically, which if you type that in your calculator, it's about 7.7. So it doesn't really make sense. The reason why they didn't put the minus, remember, whenever you take the square root of a number, it always gives you the positive and negative version of it. So for example, the square root of 16 is positive and negative 4. The square root of 32 is positive and negative root 32. But in this case, this is a real world problem. You can't have a negative 7.7, what is that, feet tall or whatever measurement of a negative value. So that's why they only kept the positive version there. So the house is approximately 17.7 feet tall. So the total height that the truck must clear is greater than 17.7 feet. The trucker should plan a different route to the site. So not only have they introduced the idea of isosceles triangles, the two properties with an isosceles triangle, and I'm going to use this as an example, If you're dealing with an isosceles triangle, the two side lengths have to be the same and the two base angles have to be the same. So they introduced that to you, but now they're also telling you that you can take an isosceles triangle, split that down the middle. That's what they were talking about on the last page. You can do a bisector of angle B, and it creates a perpendicular bisector to AC. It creates a perpendicular bisector to that base. And the reason why that's important is because now they give you two right triangles. You can use Pythagorean theorem to kind of find any missing information. So now they're talking about equilateral triangles. Equilateral triangles, again, is just another specific type of triangle where all three sides are the same length and all three angles are exactly the same. Okay, so isosceles triangle says that the two side lengths are the same and the two base angles are the same. But an equilateral triangle says all three sides are the same and all three angles are the same. So prove that the equilateral triangles are equiangular. Prove that equilateral triangles are equiangular. So they're basically starting off with a proof. Just like we've done in the past, we are not doing proofs. So any problems that deal with a proof, we're just going to skip past it. It's just kind of it's a little involved for online learning. If you'd like to work through this, you're more than welcome to kind of walk yourself through it. But I think we're just going to skip proofs altogether. Then example 6, last example, find angle measures in isosceles and equilateral triangles. So what they're giving you here in part A is they're giving you an equilateral triangle. You could tell because all three sides have that singular tick mark. And then they're also giving you an isosceles triangle. I can tell that because both of the side lengths have the same tick mark. So this is an equilateral triangle. This is an isosceles triangle. So if the measure of angle CBD, so that's taking both triangles into account. So this big angle right there. If that angle is 130, what's BAD? So if this angle right here is 130 degrees, what's this angle up here? BAD. So what they're doing, they're starting you off with the measure of angle ABC, which is that side right there. So that corner of that equilateral triangle, plus the measure of angle ABD. So that's this one right here, basically the top, or I guess, as it's oriented, the bottom of that isosceles triangle is going to be equal to CBD. So both of those angles added together. So the bottom right of that equilateral triangle plus this bottom part of that isosceles triangle are going to be equal to them both being added together. Now we're just plugging in the given information. You know that ABC is ABC, that has to be 60 degrees. And then ABD is what you don't know, but CBD based off of this up here has to be 180 degrees or 130 degrees, sorry. So since ABC is equilateral, that's how they knew it was 60. Remember, any triangle, if it's equilateral, all three angles have to be the same. So basically what they did was they took 180 degrees, which every triangle is, divided it by 3. So it tells you that all three angles have to be 60 degrees. Now that I know that, I can subtract 60 from both sides and we figure out what that missing piece of information is. So ABD, basically the bottom or the top, however you look at it. I look at that as the top. The top of the isosceles triangle is 70 degrees. Use the isosceles triangle theorem to find the measure of angle BAD. So BAD, you're looking for that kind of, I don't know, top left. Just depends on how you like to look at that, orient that. So again, what they're doing is they're taking ABD, which is the top or the very bottom of that isosceles triangle. They're adding it to BDA, so the top right of it, and they're adding it to BAD, which is the part that you're trying to find. So they're only looking at this isosceles triangle. If you add all three of those angles together, they have to add up to 180 degrees, every triangle. So what they're doing is they're plugging in what they found on that previous step. They know that ABD is 70, so they're replacing that with 70. And because this is an isosceles triangle, you know that those two base angles have to be the same. So what I can do is I could subtract 70 from both sides, and then I get the measure of angle BAD, and the measure of angle BDA has to be, what would that be, 110, right? If I subtract 70 from both sides. So if I take away that given side at the top, I know that when I add these two sides together, they have to add up to 110 degrees. Well, if I know that these two angles are congruent, all I have to do is divide 110 by 2. So I know that each of those angles has to be 55 degrees. So again, some of the stuff is given, some of the stuff isn't, but you really have to use the idea of what an isosceles triangle gives you, what properties are involved with that, what properties are involved with equilateral triangles. If you missed kind of what I said a few minutes ago, you might be wondering, well, where did you get the 60 up top, right? How'd you know that ABC was 60? Keep in mind that equilateral triangles, all three angles have to be the same. So all you have to do is take 180, divide it by 3. You know that they have to be 60 degrees each. Okay. Part B. What's the measure of angle U? So they're looking for this measurement right there. Step 1, find the measure of angle SVT. So they're looking at this side right here. It's basically that side of that isosceles triangle. That's what this is, an isosceles triangle. This is also an isosceles triangle. You can tell that these two side lengths are the same, which makes this an isosceles triangle. You can tell that these two side lengths are the same, which makes this an isosceles triangle. Okay. So find SVT. This is S, this is V, this is T. So you're looking for basically the base angle of that isosceles triangle. And you're going to use the same idea that you used up in that top example with example A. If you know that the top of that isosceles triangle is 72, and I'm going to go ahead and write this out on paper. If you know that, I'm going to keep it the same way. I was going to draw it differently, but okay. All right. So this is my isosceles triangle I'm looking at. If I know that the top of that triangle is the same, well, I also know that the two base angles have to be the same measurement. I know that an isosceles triangle has 180 degrees in it. So if I subtract that known angle at the top, I know that these two angles together have to add up to 108 degrees. So all I do now is take 108, divide it by 2, because I need those two angles to be equal to each other. What is that, 54? So I know that each of these base angles are 54 degrees. So that's the idea that they're trying to walk you through here. Find the measure of angle U. So write an equation using that triangle exterior angle theorem. What they're telling you there, where are we looking at? We're looking at U. This is U right here. Okay, so that's the angle we're looking for, angle U. They're also telling you in this picture that this side is the same length as this side, which is essentially cluing you into this blank triangle right here is also an isosceles triangle. So they're talking about that exterior angle theorem. What they mean by that is that if you have a line and something like that, right? Something like this situation that's here. If this side is 54 degrees, you know that a line altogether has 180 degrees. A straight line's 180 degrees. So this other missing piece on the right-hand side, what is that? 126. So if I know the other side of that angle is 126 degrees, again, because a straight line has 180, if this has 54, that means that has 126. And if this is an isosceles triangle, again, those two base angles have to be the same. So what I'll do is I'll take 180, subtract 126, which is 54 degrees. Take 54 and divide it by 2. What do I get? 25, 27. So I know that angle U is 27 degrees. Top of page 163. This is just the summary of everything. Let me just re-emphasize the two main ideas, which are kind of on the outside of this page. Isosceles triangle, if your two side lengths are the same, then the two base angles have to be the same. Okay, if the two side lengths are congruent, then the two base angles have to be congruent. And vice versa, right? That's that converse statement there they were trying to say. If the two base angles are the same, then the two side lengths are the same. Okay. The other one is equilateral triangles. All three sides are the same length, guaranteed. All three angles are the same measurement. And again, vice versa. If all three angles are the same measurement, then all three sides have to be the same length. The other thing they threw in here was that perpendicular bisector idea. And the reason why, let me emphasize this, the reason why they're throwing this in here is because if I create this perpendicular bisector, which is that line BD, if I put that over my isosceles triangle, then it's going to form two right triangles, right? This part right here, I wish I had a pencil on me. I don't want to draw on my book. But that part right here, that forms a right angle, right? So that perpendicular bisector forms a right angle. It goes straight off that line AC. And then I can use this idea of Pythagorean theorem, right? A squared plus B squared equals C squared. So now we're on page 164. This is going to go through the practice problems. Remember what we said, we are skipping, man, what was it? Example 5. We skipped example 5, which was all about proofs. So we are not going to do any of these proofs in this section. I just turned to this, so I don't know how many there are, but we are not going to do number 17. That's what it's asking you to do. So given this information, they want you to prove this information. The way you do that is you just use properties of isosceles triangles and you walk yourself through the proof. But again, it's kind of a lot to really master that idea of proofs online. So we're going to skip past that. If you would like to look through that though, or if you want to work through it with me, feel free to email me. I'm happy to jump on there and kind of explain each of the steps to do a proof with you. You could also look at the solutions manual that's in Canvas. And that solutions manual, I'm assuming, should walk you through each of those steps as well. So if you're interested in that, you're more than welcome to take a look at that. Find the unknown angle measures in each triangle. Get myself some paper here. All right, so number 18. Find the unknown angle measures for each triangle. The first thing you have to kind of do is look at this and see what given information they're putting on this picture. What they're doing is they're putting these two little red tick marks, which indicates that those two sides are congruent, that they're equal to each other. So I know that what PQ is equal to QR. Okay, those two side lengths are the same. And then what that does is that clues me into that's an isosceles triangle. So if I know that, right, if I know that this is an isosceles triangle, I can use those properties, that follow along with an isosceles triangle to help me solve any information that I'm missing. So in this case, this is the top of the isosceles triangle, right? My two sides come down from the top. And then, so this is my base. So in an isosceles triangle, I know that the two base angles are the same. They're congruent. So I know that angle R is 51. So for number 18, angle P has to also be 51 degrees. Okay, angle P has to be 51 as well. What about angle Q? That's the top. Well, we know a triangle has 180 degrees altogether. If the two bottom angles are both 51, I can subtract those away from 180 to figure out what that leftover amount of degrees is for angle Q. So 180 minus, what is that, 102? That's going to be 78. So I know that angle Q is 78 degrees. Number 19, same idea. They're telling me that those two tick marks that this is an isosceles triangle. If the top is 68, what they're asking for is what is angle S, what is angle U. Hopefully you're saying that S and U have to be the same, right? If this is an isosceles triangle, the two base angles are the same, they're equal to each other, they're congruent. So what I can do is I start off with that known piece of information that a triangle always has 180 degrees. They're giving me one of the three angles, so I can subtract that. What is that? 112. So both of these base angles, if I add them together, they both add up to 112 degrees. So all I have to do, since it's an isosceles triangle and the two base angles are equal to each other, I just divide it by 2 and I get 56 degrees. So both angle S and angle U are 56 degrees. Number 20, find the lengths of all three sides of each triangle. What this triangle for number 20 is telling me, since those two base angles have that tick mark there, it's telling me that this is also an isosceles triangle. If all three angles had that tick mark, it would be telling me that it's an equilateral triangle. So since this is an isosceles triangle, I'm going to use that same idea that I'm assuming they talked about in example 3, that the two sides have to be the same length. So for number 20, if this side is congruent with this side, then that means that they're equal to each other. So I'll actually just set them equal to each other. And then solve for x. So I'll add 12 to both sides, divide both sides by 4, and I get x equals 8. That's not the information they're looking for. They want you to say what the measurement for each side is. So x is just the variable number that we're going to plug in. So for number 20, they want the length of each side. So here's how you'd write that. Side length ED, right? That's 20. There's no variable there, so I don't even have to plug in anything. It's just 20. So side ED is 20, and I don't know why I wrote degrees. It's just 20 feet, 20 inches. I don't know what the measurement is. It's just 20. What about EF? So EF was 4x minus 12. So if x is 8, I just plug in 8. 4 times 8 is 32. 32 minus 12 is 20. So I know that it's going to be 20. Did I have to do that math? Absolutely not, right? We know that because this is an isosceles triangle, those two sides have to be equal to each other. So I could have just automatically said that EF has to be 20 as well. And then what about DF? That's 3x plus 5. Again, if x equals 8, 3 times 8 is 24. 24 plus 5 is 29. So DF has to be 29. 21. I'm assuming it's the same kind of idea. You're still dealing with an isosceles triangle. I know that because the two base angles are the same. So I know that the two side lengths have to be the same. So we'll start off with number 21, that, what is it, GH, the side length of GH is 45. That's given, right? We didn't have to do any math. But if we want to find JH, we're going to have to do some math. So we know, technically we don't have to do some math, right? Again, this is an isosceles triangle. So we know right off the bat that JH has to also be 45. But we're going to have to do some math for the base anyways. But let's go ahead and do that math, and we'll be ready to plug that number into the base. So because it's an isosceles triangle, we know that the two sides have to be congruent to each other. So to solve for x, we're just going to set them equal to each other. And then solve. So I'll subtract 3 from both sides. Divide both sides by 6. And I figured out that x equals 7. Again, you can also go back and plug this in, right? 6 times 7, that's 42. 42 plus 3 is 45. So we showed that those things are equivalent. They're congruent to each other. But what about the base JG? or GJ, doesn't matter. If X is 7, I'm going to use that base measurement 4X plus 1. It'll be 4 times 7 plus 1. 4 times 7 is 28. 28 plus 1 is 29. So we know all 3 lengths side measurements of that triangle. Use the figure shown for exercises 22 and 23. What is the measure of angle DEG? So what are they looking at here? DEG. So they're looking at that little piece right there above my pen. That's DEG. If the measure of angle DFE, so DFE, so they're looking at this angle right here, is 70 degrees. Okay. So there's going to be a few steps with this one. If you know that this is the, the base angle down here, the way I like to look at this is if I turn this on its side. Let me see if I can do this. Right? That's kind of how I'm picturing in my head, where that's the base and then the triangle comes up from the base. So that's how I'll refer to it. I'll call this my base and then these are my side lengths. Okay. So for 22, what type of triangle are we dealing with? Well, right off the bat, I can see that we're dealing with an isosceles triangle. The reason I know that is because that side length C, they're telling you it's side length C. It's the same as the other side. That's also side length C. So that's cluing me into, they're trying to tell me that this is an isosceles triangle. Okay. So I use those properties of isosceles triangles. What they're looking for is, what is the measure of angle DEG? So they're looking for this angle right there. If you know that this angle right here is 70 degrees. Let me go ahead and just kind of sketch this a little bit, super quick. So that's what they know, and that's what they want to find. Again, if you know this is an isosceles triangle, because they're telling you that this side is the same length as that side, they're calling each length C, okay? Well, then this other base angle has to also be 70 degrees, right? That's just a property of an isosceles triangle. Well, we know that a triangle has 180 degrees altogether. So if I've already used up, 70 and 70, that's 140. If I've already used up 140 degrees, that means that these angles, right, both of these up top have to be 40 degrees. Both of them together, they both have to be 40 degrees. Well, if you look at your picture, they're not talking about both angles together, the entire top. They split that down the middle. See how there's one tick mark above that line, there's one tick mark below it. That's indicating that both of those angles are congruent. So it's telling me that what I have to do is I have to take that measurement that I just found, that 40 degrees for that entire angle, and just divide it by 2. That tells me that that little piece that we're finding right there above that line, that piece is 20 degrees. What is the value of B if A is 8 and C is 24? So let's go ahead and just kind of plug in that information. A is 8, so A looks like it's right here. So that's 8. A is 8, there's no more A's. C is 24. So this is 24, this is 24. Any other C's? Nope. And this is what they're trying to find. Basically the height of that triangle. Again, I'm calling it the height because that's how I'm thinking about it. This is my base, these are my side lengths, so that's my height. And what they're cluing you into here is basically this line that's going across down the center there, that's that perpendicular bisector. What that did is it created 2 right triangles. So here's that Pythagorean theorem, a squared plus b squared equals c squared. So let's just look at, let's just look at this triangle. Both sides of this triangle are exactly the same, so it really doesn't matter which side you're talking about, but because they gave us that information on the bottom of this triangle, we'll use this one. So a squared and b squared, it doesn't matter which one you put where. I could do this. I could do 8 squared plus b squared, I could do a squared plus 8 squared. It doesn't matter, right? You can put that 8 anywhere with a or b. You could put that, you can keep a or b. It doesn't matter which one you do. But the one thing that does matter is the part that's opposite that right angle. That's your hypotenuse. That's your C value. You don't have a choice on where to put that, okay? So that has to be your C squared. So 24 squared. So I'll go ahead and use this one right here just because it's the one written on the bottom and I can write underneath it. A squared is just a squared. B squared, that's 8 squared, that's 64. Oh man, 24 squared. I'm gonna have to do that in my calculator. I don't feel like doing that in my head. 576. So what I want to do now that I have a squared is I'll subtract 64 from both sides and I get a squared equals, what would that be? 512, right? 576 minus 64 is 512. And now I'll take the square root of both sides. The square root of a squared is just a. The square root of 512 is a decimal, right? Pretty nasty decimal. So instead of rounding off this decimal, I'm just going to keep it as plus or minus the square root of 512. Because if I rounded that decimal, it technically wouldn't be the exact answer. But if I keep it as the square root of 512, then it is the exact answer. So did that answer my question? What's the value of B? So what that's telling you is that that your B value, I guess I should have kept that as B. I should have plugged that in for A, but it doesn't matter. What that says is that missing piece of information is plus or minus root 512. So that height of that isosceles triangle is obviously not minus because it wouldn't be a negative height. It would have to be just root 512, the square root of 512. 24, prove. Again, we're going to skip that. If you want to look at that, feel free to reach out to me or look in the solutions manual. I'm happy to go through that with you, but we're not going to do that in this lesson. 25, given the measure of angle PSR, so that's basically this bottom of this figure here, that bottom angle, is 134. What is the measure of angle SQR? So SQR. So that top right little piece right above my pen there. Let me see if I can sketch this out real quick. Okay, I think I got it. It's not perfect, but you'll get the point. So we're on number 25 now. So this is number 25. So they're saying, given that PSR, this angle right there, both of those together was 134. What's the measure of SQR? So looking for that measurement right there. A couple things that you could do. What's the easiest? I would guess what they're trying to get at here is to kind of keep in mind the properties of equilateral triangles and isosceles triangles. We don't really know anything based off of this given information of 134, but what we do know is that if this is an equilateral triangle, we can tell that because all three of these sides have a singular tick mark on them, which indicates that all three sides are the same length. Well, if that's true, then all three angles inside that triangle have to be the same measurement, right? So what I do is I just do 180 divided by 3, which tells me that all three sides inside PQS, right, that triangle there, have to be 60 degrees. So if I know that this piece right here, right, if that is 60 degrees, well, then what's the rest of that? 134 minus 60, what is that, 74? So I know that the piece on the right-hand side over here has to be 74 degrees, okay? So if the whole thing is 134 and this is an equilateral triangle, that has to be 60. So what's left over, 134 minus 60, means that that right side has to be 74 degrees. So if the I'm going to kind of draw this triangle out again just because there's a lot going on. So here's that equilateral or that isosceles triangle from above. We know that this is 74 degrees. If we know that that base of that isosceles triangle is 74 degrees, well, the other side has to also be 74 degrees. If we know that, we know that triangles all add up to 180. So all we have to do is subtract the two known angles to find out what that missing angle is. And if I remember correctly, that's what we're trying to find, right? So I'm going to subtract 74 to find that missing angle up above there. So 180 minus 74, that's 106. 106 minus 74, that's going to be 32. So what that tells me is that this angle right there, that missing piece that they're looking for, is 32 degrees.